Okay, so I guess we can start now. The ones of you who do not have laptops with you, I highly suggest you using the local computers because the structure of a seminar will be as follows. We'll first get acquainted with Torch, with some main objects, with some classes, etc. Of Torch. We'll next see the backpropagation on a simple example with derivation of all the formulas. But then we'll write our first neural network and we'll use our hands, like we'll write it from scratch. So in this notebook, we of course have the like already pre-written classes, but in my view, if I just simply scroll this, it like you won't deeply understand and realize these concepts and their importance. So after this, we'll make a lot of cells missed and we'll write the whole components of a neural network in Torch with your hands. So it's I highly suggest you that this very part we do together with you. Okay, as for the Torch, this is the most popular framework for deep learning, and interestingly, that even 3 years ago.
Can we open it somewhere?
Yeah, sure. You can use the GitHub. Well, 1 second, I'll send the link. Yeah, sure. Yeah, so while you are opening it, let me make a brief introduction for Torch. Even 3 years ago, almost 15 or 20% of users of deep learning were using Torch, and like in a year or two, it experienced a great surge of popularity because you can write absolutely any neural network of any structure very easily, and what is sometimes even more important, your neural network will be easy to understand for other users. So let's first start with some imports. Conventionally, we'll need these 2 modules, so the Torch itself and the NN module from Torch. So everything that is relevant to neural networks, to deep learning, it is contained in this package NN. We'll also need, for now, the NumPy just to see, to have a small comparisons of these libraries. So the main objects in Torch are Torch tensors, as you probably can see. And the idea is as follows. So what is a tensor? Does anyone? Okay, you all know, great. That like 1-dimensional tensor is a vector, 2-dimensional is a matrix. And of course, when we deal with neural networks, we'll sometimes need a lot of more dimensional vectors. Just a small example to understand a 4-dimensional vector. We have one image, right? So it has some height, it has some width. Let me, it's better if I write something here. Like, I don't know. Let it be a cat. And in majority of cases, it is also colorful. So for now, yeah, I only used my blue marker. I can also use some green to, I don't know, fill with space inside of it. It has some colors, and how to translate colors to the computer. In fact, there are several color channels of each image. They are named the same way. Like a conventional way is representing an image in 3 color channels. That's the red, blue, and green. Using these 3 channels, we can image absolutely any picture of like any colors using these 3 channels. So we have the height, we have the width, and we have these channels, colorful channels. Yeah, so it's already a 3-dimensional vector. And then like imagine that we're training a neural network, we're training in a mini batch gradient descent, and we have several observations in one batch. So that's image 1, here will be image 2, etc. So the fourth dimension will be n, the size of the batch. So we have n by h by w by c, and we can see this is a 4-dimensional array. So which torch greatly deals with them. So some very easy notions how to create a torch tensor the same way as NumPy from a iterable object. So from by the way, from the iterator we cannot create the tensor the same way as NumPy, but if there is at least a tuple like NumPy array range, we can create a torch tensor from it. Here you can see that if we compare them all, they are all the same. All the base functions which you used in NumPy, they exist in Torch as well, like torch arrange, reshaping, transposing, calculating some statistics like variance, mean, median, etc. Everything exists in Torch. We can also create torch tensors with some predefined data type. This is especially important when we need to deal with the memory, with the speed and how much memory it occupies. To create a tensor with d-type int8, we need to have it as torch char tensor, int64 long tensor, float 16, so-called half float. We need to have half tensor if you want to, well, frankly speaking, even I myself do not remember these all names of the class. So I only remember long tensor and simple torch tensor. If you need to deal with these types, you can see it here. But frankly speaking, you can in my opinion, it's not necessary to keep this in mind. If you need, you can Google in 10 seconds because remembering these renames brings you no benefits. We can deal better or easier like here. So instead of, again, recollecting them, we can just make tensor 2. Like you probably remember, if we want to change the type in NumPy arrays, we use the command as type. Right, and here we can use the method to change the type. Another interesting thing, instead of using the type, let me launch of this cells. Instead of using the type, we can also do the following thing. We can say transform our tensor to the type which has another tensor, like this tensor 1. We know that it has the d-type int8, and we want to have the same. We can do it this way, and it does the same thing. That's it. One nice function which I personally use a lot every day, and which does not exist in NumPy. We very often need to select top k, largest or lowest values. And unfortunately, in NumPy, there is no such function to my knowledge. So we need to make this arc sort, then take elements with respect to arc sort. Not so easy. In Torch, there is a great method, top k, which allows us to select k largest or lowest instances. If we want to have the lowest, here is the argument. It returns us to tensors with the values and with their indices. If we want to access to them, we can either use it this way, or we can use it like the first is values and the second is indices. We can do the same way. That's it. Okay, so that's for the base torch tensor object. And let's speak now about the parameters. So torch tensor is a class to store some data which we can, of course, change manually, but the one which does not need to be trained, does not to be updated, it just stores some data. And if we want to have the parameters which can be changed, we can accumulate gradients which can be modified. We need to create an parameter And one thing, just to make life easier for you, they are always need to be created from torch tensors. So we cannot create an n parameter from NumPy array from list, only from torch tensor. That's the I don't know, the caveat of this very class. The benefit, the biggest benefit lies in the fact that when we calculate some backward passes, they accumulate gradients. So let's do the following thing. We take tensor 3 as a parameter. That's the tensor 3, just not to forget it. Make the parameter. We make our loss the following thing. Let's subtract 1 from this vector. We'll have this very thing. And let's square this. So imagine that these tensor 3 were the predictions. 1 was the true value for each of the predictions. Yeah, and we calculate them as E. So the loss will look the same way. And for now, as we just calculated loss, we can see that param_grad does not return anything. It means that it returns non-object. So easy to check this. It returns none. But when we launch the backward pass, when we tell to our to torch that, okay, calculate the gradient of the loss with respect to each parameter that influenced its value, we will have the following thing. Here is the grad, like -2 for the first component, 2 for the second component. Another important thing is, I will relaunch these cells and do the following thing. Okay, let's do it this way. We'll get an error. What's the problem? The problem is that Torch for some base applications can only calculate gradients with respect to one single value. So here is the loss is a tensor for each of them, yeah. And if we try to calculate separately for each of them, we'll find the following error. Sometimes when you get this, you can just struggle to understand the reason of it. The reason is simple. You calculate with respect to a tensor, not to a value. So here I do the sum, or we can do the mean. It like depends on the task, and we'll find our gradient here. That's it. So any questions on this part? No. Okay, thank you. So let's move forward to the back propagation. Let's create a toy data set. We'll have only one feature, and the target is the minus cosinus, right, of this value. So let's try to fit a linear regression on this data. I guess this is not new for you. We fit it, we get the coefficient, and we make the prediction. And this is what we have. So if we make the prediction, that's it, multiplying by the coefficient and adding the intercept and subtract the real data, we see these are the errors. Okay. Let's now implement the same thing, but using the manual gradient descent. Under the hood, by the way, linear regression is also trained using the gradient descent. It does not use the analytical solution, but let's see it like manually on this very example. So what we need to do first, we need to initialize our parameters. The topic of initialization will touch upon this on our next, or probably, yeah, I guess on the next lecture. For now, let's do the following thing. Let's initialize the weights parameter with some value from the uniform standard distribution. To get it, we need to use torch rand. It's the uniform distribution from 0 to 1. And we'll initialize the bias coefficient with 0. Let's make our data tensors here and here. Unsqueeze method, what it does, it adds an empty dimension to our data. So applying unsqueeze command, let's see what it looks like now. I haven't launched it before. Applying the squeeze command is exactly as if we did the following thing. Probably you already used this very construction. So it's absolutely the same. Some like this, no difference between them. Okay, we make them as tensors. Let's do the forward pass. For simplicity, I named the prediction with the variable a, just to easier calculate these gradients. And we have our errors. Let's calculate the mean squared error and see the error for each of the objects. Okay, that's it. So these are the errors, of course, since this is since here we have already fitted model, and for now we have a non-fitted model, right? We simply initialize the values with some random values. The errors are much larger, but never mind. Let's calculate the backward pass. Here is an easy recap for you if you forget how to do this. And for now, I'll use the desk to do it manually with you, because simply looking at it will not provide you any knowledge. The ones who are on Zoom, please tell me if you will struggle to see what I'm writing on the desk. Okay, so as I promised in the lecture, let's derive the full gradient update rule for our simple linear regression, just to make sure that each of you understand how to make this. Okay, so our forward pass look as follows: A equal to X multiplied by V plus bias, loss equals to Y minus A transposed Y minus A. Why it is? Because we need to get only one value. Here we'll have the shape like, oops, transposed vector will look like this, transposed vector simply look like this, and we get only one value, like this is a scalar, right? That's the loss. Let's calculate the loss with respect to our parameters. So as we as we said, apply the chain rule here. So that's the same as calculating the derivative with respect to A multiplied by derivative of A with respect to V. So that's it. What we get for this very thing, we get the gradient of Y minus A transposed, easier like this for some guys, with respect to A, and here we'll have the gradient of A with respect to V. So this is easy to calculate. The derivative of this with respect to V is just an X transpose, right? Or we probably won't need to transpose. Okay, let me this way. Let's now see this very part. We can differentiating a multiplication is the same as differentiating each of these parts multiplied by the next part. So that's the same as making like this multiplied by Y minus A, plus absolutely the same for the second term. That is Y minus A transposed multiplied by minus A by A. That's it. So what we can see, we can easily derive the gradient for, like we can easily calculate this very part. Why? Because here the derivative is simply minus A, right? And here this part, it just stays stable. So we have 1 minus A transposed multiplied by minus 1, because here we have the minus. And as for this very part, we can deal with this transpose operation. Yeah, thank you. But we can also notion one interesting thing. The shape of this is, as we've already said, 1 by n, and the shape of this is n by 1. So this is a scalar, right? This is a scalar. And if this is a scalar, we can make the following thing. A transposed scalar is itself. So if we transpose this thing, nothing is going to change. So we'll do this. We get, just to recall, A B transposed means B transposed multiplied by A transposed. So let's do the following thing for our part. That will be y minus A transposed multiplied by A transposed by A transposed. Another mathematical rule of transpose operation is that if we like find the derivative of the transpose operation, yeah, we can make it the following thing. We can make it minus A by A transposed. So this is moved outside. And we also have this, the second transpose operation. So they are broken. And if we look at this, yeah, this can already be removed. We get exactly the second term, the one which was calculated there, y minus A transpose multiplied by the gradient. So the result of this step is simply 2 multiplied, yeah, exactly, 2 multiplied by 15. That's it. So the full gradient with respect to A, we have found it. That's the minus 2 multiplied by y minus A. And here we also found it, that's x. Let's see that I transposed. Everything is okay with the dimensions. Since we transposed it, it has 1 by n, x has n by k. So totally we have our gradient of shape 1 by k. Exactly, that's the size of our features matrix. Or our weights matrix, I'm sorry. So that's it with respect to A. With respect to B, it will be absolutely the same. We already calculated this. We only need to calculate the A by the B. But there is one important notion that some of you may omit when you calculate this, and then you will have problems with that. Your dimensions do not coincide. So the problem is as follows. If we calculated the following thing, like x3 plus b, and it looks like a unit matrix, right? So like here, since b is a scalar, this is also be a scalar, right? 1 by 1. Like I'm not cheating. So, but if we calculate the following thing for b, we'll have minus 2 multiplied by A transposed by this very scalar. Looks that everything is okay, but here is dimension y by n, and here is 1 by 1. And so it's not great because the update rule or gradient is of length n, while we have like it should not depend on the number of observations. It need be of the following, of the same shape as the parameter itself. The problem was on these very operations. So it's not the unit matrix. Why? Because in practice, what we do, here is a vector of shape n by 1. It's easy for us to understand how to like add a value to the vector, but in fact, what we did, we multiplied b by the unit vector of shape n by 1, so that we could add them together. So in fact, the gradient is exactly this very matrix, I of shape n by 1. So if we derive the full gradient, transpose the shapes are 1 by n multiplied by n by 1, and we get this color. That's it. That's the only point which you need to keep in mind when calculating the gradients. I don't think that in practice, in work, in real projects, you'll have to calculate them a lot, but it's important that you understand how they calculate. If some of you go to, I don't know, like research and derive some hard concepts with your hands, of course, you will need this. So don't remember that when we add a number, it's in practice, we multiply it by the vector of the same shape as the first argument. So that's it for math part of our seminar. If you have any questions, let's discuss them. Okay, if no questions, let's see this on the example. So here are these very update rules which we have derived, and let's ensure that if we calculate the gradients using torch, it will be the same as the ones which we have calculated manually. So what I do here is I simply apply this very rule. Yeah, while calculating this, I forgot this 1 divided by n, the number of observations. It can either be added or not, depending on your desire. But okay, it's added here. So we have 2 divided by 3 multiplied by a minus y10. So again, yeah, it would be probably easier on the desk if instead of this, I would say just 2 multiplied by a minus 1. Minus y transposed, right? Just incorporating the minus sign inside the brackets. So that's the formula for the prediction update. That's for our weights parameter, and that's for our biases. So let's see, for weights, we have such value of gradient. That's for the bias. And what we do now, we take the mean value of our loss, right? So we the mean value of our errors. Again, let's recall them. Here are the errors, and we make the backward pass of our loss. And if we see the gradients, yes, they exactly coincide with the values which we have calculated. Just 1 more minute to see the benefit of the gradient descent. So, okay, we have calculated the gradients. Let's make 1 gradient descent step. Here is the new value for the learning rate step, right? So what we do, we subtract the gradient multiplied by the coefficient, the same as like moving into the direction of the anti-gradient. We do this, and let's do the following thing. Let's calculate the mean value of the loss which we had here. We can derive it here, by the way. That's how it looks like. Yeah, and let's recalculate loss with our new parameters only after 1 step of gradient descent. You probably see the output of the cell. Here it is. So even after 1 step, it significantly decreases. So like by, I don't know, how much is it? About 5%, right, of the full loss. In practice, by the way, you may encounter such cases when after making 1 or even several steps, the loss even increases. That's okay. That may coincide, it may happen just because we're trying to get rid of, to get away from some local minima. The loss may surge, may increase for some time, but it's important that during several epochs, right, or during several steps, you can see that the loss decreases. That's it. That's for the gradient descent and math part. If you have any questions, again, let's discuss them. Okay, if no questions, let's move on. By the way, during our seminars, we'll try to, we are speaking about all the instructors, we'll try to show some interesting tips, which probably you did not see during the previous courses. One of them, one of my favorite ones, are the so-called magic lines, magic cells in Jupyter. If anyone knows what it is, please raise your hands. Okay, about half of you. Great. So I will just show some of them, which are the most useful. So the first cell, some inputs, what we will need. Here, I do not remember whether we'll need here or not, but anyway, let it be. What's the point? The point is that when we building a neural network, yeah, that's probably we need the same inputs. We always need NumPy, we always need Torch, like an N module, some libraries for visualization, and of course we can write this with hands each time. Okay, but it's much easier to write all of these inputs one time and then simply load it from some file. So how to do this using these magic lines, magic cells? Magic cell is the command which is applied to the whole cell, and it has these 2 percentage signs, symbols. A magic line is the one which is applied for one line, and it will have like this. So since we are applying it to the whole cell, we're using 2 of them, write file, that's the magic cell, and this is the path to which we want to save this very cell. Let's launch this. And what it does, we can see we have created a file and then imports, right? It contains exactly the following information which our cell had. And now if we starting like a blank project, right? What we simply need to do is just load and write the file to the path to our py file. Launching the cell gives us exactly what we had. So I guess it can save some time exactly when you need to test some hypothesis very often. Okay, so the next, I guess all of you are acquainted with bash, right? And that if we want to launch a bash command, we need to either put the exclamation sign in the beginning, or we can also use the following construction, and the whole cell will be treated as the bash code. So an option to name our data, to make it quiet, and let's download it and use this very data set. Okay, so we have downloaded it. Let's read. That's how it looks like. It's, as you can see, the housing data. By the way, is it visible on the screen, or should I увеличить нужно? Okay. Hope it's visible now. Make it even more. Okay. So the first thing we need to do, for now we won't deal with categorical features. By the way, running in advance for neural networks, dealing with categorical features is the same as for linear models. We can, if we want to save as much information as possible, it's better to use one-hot encoding. But if we need to shrink this feature dimensionality, we probably need to use some counters or some other techniques for dealing with them. So for now, let's just throw them away. We'll use only integer and float types of features. That's it. Let's also remove some useless columns like ID, which just coincides with index, right? And the target value will be the sale price. So our goal will be to predict the so-called fair price for the building based on all of these features. This is, I don't want to stop here because these are all pandas comments. I hope you all know them. Just to fill the missing values with the mean value according to the column. So if we apply the fill not to the whole data frame and pass here a dict or a series is just an advanced dict, right? It will substitute with mean value for each column. So non-values for these columns will be substituted with its mean values and so on. And let's transform all the features to NumPy float 32 type, since the neural networks are mostly attained to work with this type. This is our target value, and let's make the train test split. The last 3 cells, which we will inspect and then start coding with our hands, the standardization, the scaling of our features. It's really crucial when we apply neural networks for tabular data to scale both the features and the target value. And for features, sometimes it's okay even if we do not apply this. Of course, if we combine our network with regularization, it can like zero some important features. We can find such an image. But if we do not scale the target value, that becomes really awful, since either we need to initialize our parameters differently from the way they're initialized in Torch, or we'll have a drastical like gap in our quality. And we'll also see this today, how important is the scaling of the target variable. Some constants which we will use. I will not speak about them now, like when I will introduce them, I will describe this. And let's make another split for train and validation. For neural networks, in 99% of cases, it's crucial to have this validation sample, and early stopping is really important for neural networks. The only cases when we don't need this validation sample is probably cases when we have extremely low amount of data, cases like active learning, when we like every instance is of high importance for us. But again, it can be applied only in conjunction with some deep pre-trained models which somebody used before you. If you're using your custom own architecture, it's like crucial, I would say, in 100% of cases to have it. So making the split and start building our network. The first thing which we'll write now is the object of class data set, our arbitrary data set. The idea is as follows, that how to give the data, provide our model with the data. As we already discussed, we'll use the mini batch gradient descent. For this data, it's like a toy data set, and it has a very small number of observations. So in fact, oops, I forgot to do this. In fact, if we omit these batches and we'll calculate the gradient with respect to the whole train sample on each step, it will be even okay. But we know that generally that's not okay. And we need to divide this into batches. And there are some important aspects of dividing into batches. The first aspect is as follows. During one epoch, we should, the model should see and should be trained on each instance exactly once. If we want to make instance importance, that one instance should be paid attention to more than another, we can use the weighting, we can use tell it directly to our model, but on each epoch step, we should iterate through each object exactly once. That's the huh?
We can make copies of objects and pass one object several times to one batch.
Yes, we can also do this thing, but it will add some more time since we need to pass through more objects. And if we increase just the weights and calculate the loss properly, we will not have this time bottleneck. Okay, we need to pass. Let it be batch size. Which value is there? Okay, 64. We know that 934 is not divided by 64, so some batch will be a bit lower size. That's okay. We can, by the way, do this manually. There is another problem. It was found out that when we train, if we do not mix our batches, if we each time, the first batch is the first 16 instances, the second batch is take instances from number 16 to 32 and so on, it will slightly harm the process of training our neural network. Problem is as follows, that it will see the exactly the same batches, and it will move into the same directions each time. If they're not mixed, it can really ruin the performance of your model. So it's also important to mix the batches on each epoch. Of course, it can be done manually, but what's the purpose if there are great methods in Torch? And now we'll see how to deal with this. First, we need this dataset object, which will store our data. How to write this? Let it be my dataset. First of all, it needs to be inherited from Torch dataset object. Here we uploaded, you can see Torch utils data dataset. That's it. It should have 3 methods generally, or in some other cases, it can also have just 2 methods. I will speak about this a bit later. The first one is method init, how to initialize our object. It can either like get one array, which has both the target value and the features, or of course, it's usually easier when like we separate them. So like the arguments are, you can write the ones which you want. First of all, when like we initialize our class, don't forget to make this magic call. Does any one of you know what it means? Huh? Yeah, exactly. We need to initialize the parent class using the super calls the parent class, this one, and the init initializes it. Then we need to store our data. Yeah, so let it be like this. And that's it for init. So base dataset classes should have 3 methods, as I already said. The first is length. So all of you know what it means to write the class with 2 underlines before and after. Yeah, so like len, for instance, is when we call this function len, it let's make it this way. That's the same as if we would do this. It just calls the following method. So we need to know the length of our data set. Let it be like return len self wide. And the last one, this should be the method getItem. GetItem is called when we use the square brackets, like for dictionaries. It should have 2 arguments, self and key. Not key, IDX. And what it should return in an arbitrary format, you like will see later why in arbitrary, as you wish. You can either like you need to return the features vector and the target value for this very observation with this IDX. So we can either do it like this, return it as a tuple, or we can return it as a dictionary. It doesn't mind. The main thing is just for you to recall this. However, if we want to make a data set for some, for instance, like when we're making online requests and we do not have the length of our data set, we do not have access to it, we can substitute these 2 methods with just one method, iter. So it should show us how to iterate through different objects of our dataset, but it's used really extremely rarely. That's it for the dataset. And now we'll have the next Torch class. That's the data loader. You could probably see here we downloaded both of them. The data loader is that very object which processes which like takes the IDX from the data set, then concatenates them and returns batches. And moreover, after it iterated through all of the stored instances, once it mixes them up. So the logic which we need to adapt for neural networks. Let's see how to make the data loaders. So train data loader. By the way, it does not have too much arguments. The first one will be need to be an object. It should be an object inherited from dataset class. And it, like for now, let's make it my dataset from our X train and Y train. Yeah, so that's it. Which other arguments does it have? batch size, the size of the batch to return by this data loader, we have this constant, right? Let's make it like this. The next argument, shuffle. Yes, for train, we need to shuffle. For evaluation datasets like validation or test datasets, we do not need to shuffle since it will not affect the performance. But for train, it would be important to shuffle. Number workers, sometimes you need this argument to specify how many CPUs from your computer, from your server you want to use for preparing the batches. I don't think it's used very often. Collate function, we'll speak about this in the second module when dealing with NLP. If it selected K instances, right? And it forms a batch from them. If before forming the batch, you want to apply some other function to these very objects, you can use this collate function. An example is as follows. Let's imagine that our data set stores the texts and some target values. The texts are of different length. And if we take each of them and try to concatenate them, right, they will be of different length, but the torch tensor is has strict fixed dimensions. So it will output an error that I cannot create a tensor since I have different dimensions. So for these very purposes, we would need, for instance, a so-called data collator function, which pads all the values to the maximum length to make it a tensor. For now, let's forget about this. There is also one argument called pin memory, which, to my knowledge, it's considered to be used when you train your model on GPUs. It accelerates the process of preparing the batch, but since my computer lacks GPUs, we will not use it here. So that's the train data loader, and let's create the validation data loader and the test data loaders. The difference will be here. Here and in shuffling, we do not need it. And by the way, yeah, for batch size, again, when for evaluation data sets, the batch size, except for some rare cases like text generation, the evaluation batch size is larger than the training batch size. And the reason is that when we have our training process, we need to store both the forward pass of this batch and the backward pass. When we do the evaluation step, the backward pass is not needed. We do not use it. And in this regard, we can just increase the batch size in 3, 4, 5 times. That's okay. So here, for instance, the batch size is 64 and the eval batch size is almost 5 times larger. That's okay. And just that's not necessary, but my tip, it's easier when we have the following thing. We can make this a dictionary, train data loaders, and name them train, val, in order just not to have this big amount of variables and then forget about some of them. We'll have store all the data loaders in a simple dictionary. Okay, we're done with this part, and now probably the most interesting part, writing our first neural network. So before we move on, if there are any questions for this, for preparing the data. No questions. Okay, so let's write our first neural network. What's the how to make this? We name this as we want, like model. The first requirement is that it should be inherited from an module. Why? Because this very class, it contains the methods and the rules for computing the backward pass, for some other methods which will be called while training the neural network. So we need to inherit from it. We need to define 2 classes, the init class and the forward pass, how to make how to transform the input using our model. That's it. Only 2 methods which we need to write our neural network. So we initialize, if there are some hyperparameters, we need to set them. For instance, we need to set the input size. Now we'll see why. We also need output size, probably that's it. Sometimes we need the hidden size. The hidden size is called the dimension of the hidden layer or hidden layers if there are several of them. For now, we'll use some predefined values. Okay, let's see why this is important. Let's make our neural network the following way. So here is this. We have our input data of some fixed shape. I mean the fixed number of features. Let's make one linear transformation, then one activation function, and the last linear transformation, which will be the output. So this is the simplest neural network, right? With one activation. It is sometimes called a single layer perceptron. So we need to define the linear layers, this and this. But to define them, we need to know how much parameters are contained in X. Because if we first input the matrix of shape like n by 10, and on the next step we'll try to input n by 20, we need to multiply these by learnable parameters, and we'll have an error because we will not have this number of parameters to multiply. There will be a dimensional error. So what we need to define when initializing linear layers: the number of input units, the number of output units. The same here. A question for you: what do we need to define when initializing the activation function?
The size of the vector, like the number of output nodes in previous layer.
Okay, for what reason?
Or nothing.
Yeah. Yes, exactly. Activation function is just a function. It's I don't know, ReLU, sigmoid, hyperbolic tangent. It just transforms the data according to some rules. So there are no parameters in activation functions. So we need to define this. By the way, this in and this in should not coincide. Oh, they can coincide, but these two need to coincide to make the matrix multiplication. That's it. So let us have the first linear layers, FC fully connected, and then linear, the input size and some hidden size. So hidden size is a hyperparameter, and it's almost impossible to find out which vector is better, which value is worse. Some general tips about setting the hidden size. It's in most cases, and I personally think in all of the cases, it's useless to transform into some larger dimensions. So if you had the input of size 50, there is no reason that we would use here some values like 100. Why? Because we have the information stored in 50 values, and how would we make it stored in 100 values? Okay, we can do this, but we will not get any more information from storing large values. So there is some conventional way which says that if you don't know the desired value, use the squared value of the input size plus output size. So let's define it here. Hidden size is input size plus output size in the power of 0.5. That's making the square, taking the square root. Okay, so that's the first linear layer. The activation function, let's use the ReLU, the simplest and the fastest. And by the way, yeah, if we make it as a class, like callable object, not callable object, but if we want to use a class, we need to use like initialize it as well. If you want to define it as a simple function, we can use it like this. But we'll see like there is absolutely no difference between using these two concepts. So the activation function, the output layer, it looks like hidden size as an input and output size as an output. Okay, that's our model. Now we need to define the forward method, the one which defines how the model transforms the data. Then the argument which it takes for now, that's the x, if we want to simply transform the data. But when we will write further our personal trainers, so-called, sometimes we need to define y during training, like setting like this. If it's passed, okay, let's calculate the loss. If not, like only return the output values. So how will we transform our data? First of all, we apply the first linear transformation, then we apply the activation, then we apply the second transformation. That's it, nothing specific, same as we have discussed. So that's the class of our model, and let's initialize it. We need to set the input size, that's the shape of our train matrix, right? Train shape 1. And the output size is 1, since we are dealing with a regression task. That's it. Yeah, of course. I made an error here. The sizes should be integers, all of them. Yeah, thank you. Of course, I told about this and forgot to do this. Here again, we are obliged to initialize the parent class. Yeah, so that's our model, and just a few decent methods. So method parameters will return an iterable of all the model parameters. This is generated. If you want to output them, use the list, and we'll see. That's the parameters which our model contains. So that's the first tensor, that's the first bias, that's the second linear transformation, and the bias. If we want to have them named to better understand like which parameter it is, we can use the method name parameters, and it outputs FC, since we called it like this here, weight, FC, bias, and so on. We can see them here. A lot of other convenient methods we'll see further. For now, we have defined the model. Let's define the loss function. Sometimes it's called the criterion. So we are dealing with an MSE task. We can either like write an own custom function, or we can use a predefined function, MSE loss, from an end module. Again, we need to initialize it. The next is the optimizer, the object which will make the optimization according to some rules. For now, let's use the simple gradient descent. It's important from torch optim. Here, let it be SGD. What does it need to have as an input? First, it needs to get the parameters, either the generator, the iterator, anything like the parameters which it will update. So passing here model parameters. And the second, it needs to have the learning rate. So we have this constant LR. That's it. Depending on the optimizer, we have some other hyperparameters like momentum, weight decay, dampening, using Nestor for not. Let's set the weight decay. For SGD, it coincides with L2 regularization. That's it. Sometimes we can also use the scheduler. This is an object which transforms the learning rate of the optimizer. For instance, if we want to reduce our learning rate throughout the time, right? We can use some schedulers which reduce them either exponentially, or we can use some triangular learning rate schedulers which first rise and then gradually reduce. For now, let's like omit this. I don't think we'll. No, okay. Let me write this class. Probably we won't use it. Torch, Optim, scheduler, and here we can find. No, here. I forgot Optim, LR scheduler, and here, for instance, the exponential LR. It needs to have the optimizer as an input, which will be scaled, and some hyperparameters of the method. For instance, here we have the hyperparameter gamma. Let's set it. I guess that's all. Let me see. Yes, exactly, that's all. One good tip is to fix the seed before setting the model, since like if all of you want to have the same values as me, if we fix the seed, we'll have absolutely the same results since the initial values will be the same. Also, one method which I haven't spoken about is when you train your model on GPU, you need to transfer both the model and the data to this GPU. To transfer model to GPU, we simply need either this command, model CUDA, or we can use it like this, and here set the device as hyperparameter. For instance, for my case, I do not have GPU, the device is simply CPU. So like this line will do nothing, yeah, like a general line. Okay, so let's write our train loop. We'll write the simplest train loop ever, and after this we'll just I will get the full this cell from the bottom, and we see some interesting notes about the training. So how to make this custom loop? For n I in range epochs, we need to train our model during some fixed number of epochs. Let it be like I epoch so that we know what it refers to. On each epoch, we first need to make a forward and backward pass throughout the whole training data, and after this, we need to make the forward pass throughout the whole validation data to measure the quality on the validation set. So let it call this way for stage in train val, right, for each of these stages. On the next class, we'll speak about some special layers like batch norm and dropout, which have different behavior on training and on evaluation. And it's important that when we do the evaluation, we do not forget to move them to the evaluation mode. So let's imagine as if we have such kind of layers. For our case, it will not affect, but like generally, it's very important to always keep this in mind. If stage equal to train, we need to transform all the layers of our network to the train mode. It's done by the following command. Else, we need to transform to validation mode. That's it. Okay, another difference between the train and validation phases is in that while making a forward pass to training data, we need to calculate gradients. While doing it for validation, we do not need to calculate gradients. So if we want to pass through our model without calculating the gradients, we can use this command with torch no grad. And after this, everything which will be done like below this command, right, it will not calculate gradients until we leave this loop. But we can do this here if stage equal val torch no grad, but that's not convenient. For me, such a method seems much more suitable. With torch either true or false. If true, the grad is enabled. If false, it's not enabled. So we can pass here this very condition, stage equal to train. So it will be turned on during training phase. Okay, if we're dealing regardless of what we're dealing with. For batch in data loader, since we store the data loaders in a dictionary with these keys, we can do just the following thing. So depending on the stage, it will query us the proper data loader, either train or validation. For each batch here, we first need to make the forward pass, like output, as you wish. We need to like forward pass through the model. We can make it like this, but it's better if we do it just like this. The reason is that when using this call method, it incorporates the forward method of the model, but it also like is suitable for training on multiple devices, on GPU devices. So just remember, when we want to make the forward pass for our model, after defining it, we just need to call this. So model, let's recall how we return this. We return this as two objects. So in fact, when we iterate through the data loader, let's see it on an example for batch in train TL break, and let's see the batch. It also outputs us two tensors. This is the X with the number of observations equal to the batch size, and here is the Y. We can assert this 8 like height, 8 width, so 64 observations in total. Let's reload this. Okay, so let's pass through the first object of batch, since this is we can do it even probably more neater, is equal to batch. That's it. So we pass through the X through the features. What we do next? We calculate the loss. So loss is applying the loss function to our objects. So to our prediction, I'm sorry. An important notion is when you use some metrics from scikit-learn, some metrics which are asymmetric for real values and predicted ones, for instance, cross entropy, right? The first argument, you used the true values. It's highly important to keep in mind that when using like inbuilt torch loss functions, we always need to have the predictions as the first argument. Otherwise, the loss will not be computed. So the first argument is our predictions, and the second is the true values. That's the loss. Okay, we've calculated the loss. Let's launch the backward pass. After this, the gradients will be stored. But let's remember another crucial thing. The gradients in Torch by default, they are accumulated. So what do I mean? Let's get back to our example here. We had these gradients here, and let's make another forward pass. Like again, we do this, and again, we calculate the gradients. We had these values, and now okay, 1 second. Recalculated because I set them as nuns probably. Okay, let it do this way. We initialize. Okay, I changed these parameters. That's why I can. Okay, so the idea is as follows. It accumulates the gradients. So if we do not zero them after current iteration, the second gradient will be summed up to the previous. So before making a backward pass, before calculating the gradients, make sure that we have zeroed all the previously stored gradients. It's done with the command optimizer zero grad. Zero is the grads for all the parameters. Make the backward pass. The gradients are now stored, are now like updated, and make the step. So update all the parameters with respect to the update rule of our optimizer, our learning rate, and some like hyperparameters where decay is, by the way, incorporated here. like the peculiarity of weight decay is in that when we use the L2 regularization, we add it to the loss, while weight decay is added directly to the update rule. If we use the scheduler, which modifies the learning rate, we should also make the scheduler step. So it will update the learning rate on this iteration. So that's the easiest training loop. But if we want to collect our calculate the statistics, not for the batch, but for the whole like set on the current epoch, we need to store this loss somewhere, right? So let it be losses. Bless you. So one loss for train, one loss for validation. And we need to do the following thing if we want to accumulate them losses, stage, right? And let's add the loss value. By the way, this very loss value, it is already, like if calling some inbuilt functions, it is already averaged. So if we want to have the sum, just multiply by the number of observations. And to derive this value from the torch tensor, if this is a scalar, we need to call the method item. So like, let's recall this tensor 3. If we want it not to be represented as a tensor, but as a single value, just taking the item will suit us. That's it. Okay, so after we make this pass for our stage, let's say epoch, stage, losses stage, and round this value up to the 4th sign after the dot. That's it, formatting, and don't forget to 0 the loss after it. But one important thing, if we're doing the train cycle, that's okay, but if we're doing the validation cycle, as we've already discussed, these steps become unnecessary because we do not want to make the backward pass, to update parameters, we only need to evaluate the model. So let's add this thing, stage equal to train. Hope I did not make much mistakes. Yeah, that's how it looks like. We can see that it gradually learns something here. Let me relaunch this cells to make sure that all the data is correct. Okay, so that's how it works. It gradually reduces the values. That's it. By the way, I consider some large values, but okay, let it be this way. We can see that on validation, right, the quality also, like the loss also decreases from epoch to epoch. We can observe it here. One moment which will be discussed on the next lecture, but for now, let's recall this. For 95 or probably more % of cases, as an optimization algorithms, it's better to use Adam V. That's the modification of Adam with the weight decay. It simply provides better quality since it makes much more stable and like powerful optimization. Let's change it here. Oops, and we need to reload this. And we can see that, well, the value, not drastically, but it changed a bit more comparing to SGD. Don't remember, I probably somewhere forgot. But of course, when calculating the loss, I forgot to scale it by the number of observations. That's it. To calculate the number of instances on each stage, like we had our data loaders, right? Data loaders train, for instance, which was initialized using the data set class, right? So if we do this, it will output us the number of batches which can be used for this data loader, 15 like batches here. But if we want to get the number of observations, need to do this dot data set. So if we do it like this, the values are a bit more decent. I will reload the cells. Yeah, we can see that it decreases. That's it. So that's like the simplest, but anyway, that's the like rule of writing the training loop. Let's see a bit more advanced version, which I wrote before the seminar. So again, such a loop, if you want to use it, and a lot of users prefer using their custom loops instead of using some pre-built loops, because like you have a lot of more freedom, you can make a lot of more different, I don't know, transformations, apply different functions, etc. So it's also better to store them in a file. Everything the same here, except for we'll have the matrix dict, which will be beautifully updated using these inbuilt IPython functions. And I also appended here the part of with early stopping. I will not stop here for now. You can have a look at them like later. The idea is that it applies this early stopping. Early stopping says as follows: if during k epochs the quality on validation set does not increase for at least epsilon, then move back to the epoch which had this best quality and output this model. So that's it. Two methods which you can find here, which will probably be new for you. These are the methods again of an N module object. That's the state dict. It's the dictionary with all the parameters, hyperparameters, values, and so on, everything that can that is stored inside the model. And method load state dict. So if we want to reload all the parameters of our model, load them from some file, use the load state dict function, and here we need to provide the state dict. That's it. Okay, I'll reload this. And that's it. So it's trained, and we can see that on epoch 4 it gets this RMSE 361, right? And after during 5 epochs it do not like decrease, so we stop the training process. Here is a plotly visualization. Just 5 minutes of your attention, because some very important notions I left for the end. So that's the, I don't know whether many of you use Plotly or not, but I'll try to use it in our seminars. It's much more convenient. It's first of all more beautiful, and it's convenient since we can iterate through the objects like interactively, right? Here is an eval loop, just the same as we did in our training loop, just for evaluation, to make sure that we do not calculate gradients and so on. Let's calculate the quality. Okay, I've already trained it. Pardon. Let's calculate the quality for validation and test sample using the original numbers, because we made the scaling, and of course the values which we get after scaling, they are not so representative. So like we do not know whether this value is decent or not because we scale the target value. Let's get back to the original order, and that's it, the quality on validation and test sample. Again, we need to compare it with something, whether our model performs well or not. Let's compare it with linear regression and its modifications reach and lasso. And again, since we do not know the exact optimal lambda coefficient, let's use the classes which automatically find the optimal alpha. So lambda, yeah. Launching this gives us the best model on test set is without regularization, 38,000. So we decrease the error using just the most simplest neural network ever by 16%, right? I guess that's a great benefit. And the last important point, which I promised to show at the beginning of the class, if we forget to use the scaling for target variable. Okay, that would be this way. I will reload this. Only for target. Just we still have it for our features. Do this and then reload this, and let's increase the number of epochs just in case it's necessary, because if it's unnecessary, okay, early stopping will show us, but in case we require more epochs. Here we required 4 epochs to make the optimal model, right? So that's what it happens. As far as I remember, I need to train it for 1000 epochs or something like this, but the point is as follows. It takes a lot of more steps, and okay, let's make it so that I'm not the liar. The idea is as follows, that it will lead us to significantly worse quality. The problem is again in initialization of the parameters. Okay, so probably it stopped decreasing somewhere here. We can test the quality. That's what we had. And this is, okay, I need to schedule false, since no scaling is done now. And that's the quality which we get now, which is even worse than the simple logistic regression. So that's my point. When working with tabular data, do not forget to make the rescaling. Okay, so for now, that's all. If you have any questions, let's discuss them now at the proper time.